Hi, today we're going to learn about the properties of tangents. We already know what a tangent is. It's a line or segment that intersects a circle in one point, which is called the point of tangency. So the first thing we want to look at is why could a secant not be considered a tangent? This is because a secant intersects a circle in 2 points, while a tangent only intersects a circle in 1 point. So if we had a secant here, it would go inside the circle. It wouldn't just be touching it at 1 point. So the tangent line for this drawing is line SV, and the point of tangency is point S. We're going to look at a couple different types of tangent relationships. Two circles can have a common tangent. Common tangent is just a tangent line or tangent segment that touches two circles. A common tangent can be split into two categories, an external tangent or an internal tangent. In this example, segment PQ is a common external tangent because it's outside of the circles. It's not going in between the circles. In this example, segment EF is a common internal tangent because it does go inside the circles. So common external tangent is outside of the circles. A common internal tangent goes in between the circles. For a common tangent, you're focusing on the tangent line itself. For these two examples, we're focusing on the circles. Externally tangent circles are two circles that are outside one another, but they share a tangent and 1 point of tangency. It's kind of like a figure 8 here. These two circles, G and H, are sharing the point of tangency, point T. Whereas internally tangent circles are tangent, but one circle's inside the other. So circles A and B are internally tangent, and they share the point of tangency, W. Our first big idea is that tangents always form a right angle with a radius. And if you know a segment is perpendicular to a radius at its outer endpoint, then that segment has to be a tangent line. So let's go ahead and label this circle C. That's the name of the center of the circle. And we're going to draw radius CR. And it doesn't really matter where I draw this. Let me draw it to the side here and label that point R. And then we're going to draw a tangent line TL with a point of tangency at point R. Let's see how straight I can go here. Not too bad. So this is going to be tangent line TL. Now what this big idea says is that anytime you have a radius intersecting a tangent line, that it's going to form a right angle. What that big idea is going to allow us to do, if we look at our next two examples, it's going to allow us to create some triangles. So in example number 1, we have radius RO, and we have this tangent line OT. We know that OR is 6. OT is 8. And we're looking for RT and ST. Now, since we know from our big idea that anytime a radius intersects a tangent, we know we have a right angle, and we can use the Pythagorean theorem to find out the length of RT. So if we do 6 squared plus 8 squared, that would be 36 plus 64, and we would get 100, and then the square root of that is 10. So RT would have a length of 10. And then we're looking for ST. A lot of times students think that this is exactly the halfway point, but if you recall, we know the radius here is RO, and all of the radii in one circle are the same. So RS is also 6, and if this whole segment length is 10, we could subtract, and we know that ST has to be 4. In example 2, again, we know that we have a right angle here, making this a right triangle. We're also told that angle OTR is 45 degrees. And if one angle there is 45, then the other has to be 45 to make 180 for the triangle. So that is making this a 45, 45, 90 right triangle. And we do know here that OT is 7. And since this is an isosceles right triangle, we also know that OR is 7. And we can do either the Pythagorean theorem in this case, or do our shortcut for a 45, 45, 90. So we can put a 1, 1, and the square root of 2. And we can do our process, divide in and multiply out. So either one of these sides, we can do 7 divided by 1, we get 7. And 7 times radical 2 means that segment RT is 7 radical 2. And we could do the same thing if we had a 30, 60, 90 triangle as well. Our next big idea is that if we have tangents to the circle from the same point, their lengths are going to be congruent. So for this example, we have 2 tangents, KN and KI. They're going to the same circle. We want to mark those as congruent. Those 2 line segments would have the same measure. So our points of tangency would be point N and point I. And we can draw our radii to them. And we know from our last big idea that that makes these right angles. And then if I draw one more line here from H to K, I've now formed 2 right triangles. And they are congruent right triangles. So H and K would be congruent to HIK. And if we think back to when we learned our triangle congruence methods, these 2 triangles would be congruent by HL, by side angle side, by side, side, side. So we have many ways to prove that they are congruent. Right, for these 2 examples, we're going to use the tangent relationship that any 2 tangents drawn to the same circle are congruent to find our missing lengths here. So we know that HJ here is 36. And we know that JE is 16 and GF is 25. So we're first going to look for HG. So the thing that I do first is I know that J to E is 16, and that means that J to I is also going to be 16. And if G to F or F to G is 25, then F to E also has to be 25. We were given here that HJ was 36, and if this part is already 16, then we can subtract, and that will tell us that HI is 20, and that means that HG is the same. It's congruent. So HG is 20. HI is 20. JF, I can simply add 16 and 25 to get the length of JF. That's 41. And then IJ, since it's congruent to JE, is 16. In example 4, we know that PN is 20, and it's on the diagram here that LQ is 13. So the first thing I know is that right here, these two segments, PQ and LQ, are congruent, so that would be 13. And since PN, excuse me, PN is 20, if I subtract 13 from that, I know that QN is 7, and that means QO also has to be 7. And LO would be 20 as well. So to recap, our big ideas from today are that two tangents to the same circle are congruent, and anytime you have a radius drawn to a point of tangency, it forms 90 degrees.